Yeah, very good morning. Am I audible?
Yes, sir.
Okay. And I think screen is also you are able to see, right?
Yes, sir.
Oh, yeah, I think we can start now. So, the last session, we have seen two examples. Okay. And in one of the example, uh, the substitution method works, right? And one of the in another example, you have to be careful in deciding the substitution method for finding the extreme value of a function f subject to constraint. Okay, so a constraint so far we have taken. Okay, so there may be multiple constraints. Okay, now to see what we can do more geometrically is in this. Let's go back to the same problem and let's look at the graph here. Okay, so what we are trying to, so in the particular example, we are trying to find out the point which is on the surface, which is closest, okay, to the origin. Okay, we want to recognize point, okay, on the surface. So one surface, two surfaces, right? Because x equals to plus minus square root of z square plus 1. So we want to find out a point or points. So there may be multiple points which may be equidistant. Okay, so that we have seen plus minus 1 comma 0. Okay, 1 comma 0 0 0, right? The closest point, okay, which is lying on the surface and closest to the origin. Okay, now what we can do alternatively is we can, so this the point at that surface which we are looking subject to constraint, that is x square plus y square plus z square. Okay, so how does this looks like? This is shortest distance formula and all, that's okay. But the thing is, it looks like it's a part of sphere. If you look, if you put it like sum equals to a square, is going to be the equation of sphere centered at origin with radius a. Okay. So what you can work is like a bubble, okay, of a soap. Okay. So at the center of the origin, you can draw a sphere, and which will go and enlarge as long as it touches the surface. Okay, so this sphere is going to be enlarged. Okay, enlarged in such a way that at the end it will touch the surface. That's geometrically is fine. Okay, so that can be drawn. Okay, now what you can look at geometrically here is that, see, at any point, so you are interested in the point which is closest to the uh, you are looking at the point on the surface which is closest to the origin. Now, in other way, just now what we have drawn new geometry means like we have drawn a sphere, okay, centered at origin and which touches the surface. So what you can recognize is here the normal to this sphere, okay, and normal to the surface. Okay, so the surface is somewhere x square minus z square equal to 1. Okay, it was 1, right? Okay, so that whatever. Okay, so you have the sphere or subject to the whose variables are subjects to the constraint g of x comma y comma z equals to 0. Now, what you can recognize here at this point, which will be closest, which is going to be touches, okay, which will touch the surface at this point. So that the normal to the surface, both surfaces will be parallel. So grade f, so will give you the normal at any point of the sphere. Okay, so grade f at that point of extremum p naught must be parallel to the grade g at the p naught. P naught that you need to determine. Okay, so when you know these two vectors are parallel, you know that it's going to be scalar multiple of the other. Okay, so means in particular you are going to have the following type of problem. Okay, that gives rise to the solving the following type of problem. So where this scalar lambda will occur into the picture, which is known as Lagrange multiplier. Okay, so this is what the Lagrange multiplier method will do. We will come back to if you have the multiple constraint. Okay, so if you apply this idea here, okay, if you apply this in same idea here, this just now we have discussed. Okay, so that can be now sort out. Okay, now means you don't need to worry about the now what which variables you will take independent and which variable you will take dependent. Okay, so the alternative method you can say. So alternatively, just now we have seen, or you can say geometrically, what we see that grade F must be parallel to grade G. Okay, and so implies there exists a lambda scalar. Okay, some scalar. Scalar means a constant. Okay, scalar such that grade F equals to lambda times grade G. Okay, now if you recall, I'm just writing in this side f of x comma y comma z equals to x square plus y square plus z square. And that's the equation of the circle, sorry, sphere. So you can, we don't know that, but it doesn't matter if you differ it by a constant. Okay, it doesn't matter. Okay, you are trying to identify this A. That's it. Okay, so and g of x comma y comma z, if you recall, that was x square minus z square equals to 1. So x square minus z square minus 1 equals to 0. So now you can add it. Now I'm assuming that now means you are now quite comfortable in identifying what will be the gradient f, all components and grade g. Okay, so I'm directly writing the grade f, okay, on the left side, and also I'm directly writing the grade g on the right side by looking at the function. So grade f, I component is nothing but the f partial derivative with respect to x, that is 2x, plus grade this f with respect to y, that's going to be 2y j, plus f with respect to z, that's going to be 2z z, okay, k component, that's equals to, that should equals to lambda time grade z. So g with respect to x is 2xi plus g with respect to y is 0. G with respect to z is minus 2z. Okay. Okay. Now you can compare both sides. Okay. So what we observe, this implies, I think this implies this true. This is true. Above is true. Above is true only if what when you have the ith component should be equals, j components also should equal, k components should be equal. Okay, so that will give you 2x must be equals to 2 lambda x. 2y equals to lambda times 0, that is 0, the second equation. The third equation is 2z is equals to minus 2 lambda z. Right? Yes, minus 2 lambda z. Okay, right. Now, this first equation will give you, I mean, see, this will give you. So from this equation, what you can have, that's going to be y equals to 0. That's from there, it's very clear. Okay. Now, from here, what you have, these two will get cancelled. Z equals to or minus lambda Z. Okay. Now, from here, what you can observe is X equals to, if you take X is non-zero, see, this is why I'm taking X is non-zero. Why? Because of the equation of the surface, okay, which tells you that X can never be zero, because you can look at the equation. Okay, you can look at the equation, that is x square minus z square equals to 1. That's only possible when x is non-zero, at least, because x square is equals to 1 plus z square. So it's strictly greater than 0. It will never be 0. From here, I can certainly observe z could be possibly 0. Okay, but x square will never be 0. So where that condition can be easily guaranteed from here. Okay, so x will never be 0. X is not 0. It's very easy to recognize that. So then certainly you have lambda equals to 1. So now, but this third equation, so thus this third equation, z equals to minus lambda z, when it will be true, when lambda is 1, so it means z equals to minus z. When it is possible, whenever this z is 0. So this will give you all the possible. So you have the values will be, so from here, so what you observe is follows: lambda equals to 1, y equals to 0, and z equals to 0. These three things, and x is non-zero. So you are seeking the point x comma y, x comma 0 comma 0 on the surface. Now, on the surface where, so you have the surface equation is, it should satisfy the equation what, x square minus z square equals to 1. This point should lies here. So when this point lies here, x is non-zero, you have z is 0. This implies x square equals to 1, and that will give you x equals to plus minus 1. So the points are nothing but plus minus 1 comma 0. Now, in any case, x equals to 1 or x equals to minus 1, f of x comma y z will always be 1. Okay, and also we have already seen that f of plus minus 1 comma 0 comma 0 is equals to 1 unit distance. Okay, right? So now, okay, now you have the closest point. Okay, right. So this is known as the method of Lagrange multiplier. This is the approach of method of Lagrange multiplier. So I would like to summarize here that what actually we have just now discussed. Okay, right. So, so I'm just summarizing the things. So the method says that the extreme values of a function. See, we are talking about the gradient. So it must be assumed that f has all the first order partial derivatives exist at least. Okay, gradient is required the existence of the first order partial derivatives all. Okay, very simple. So the method says that the extreme values of a function f of x comma y comma z, whose variables are subject to a constraint g of x comma y comma z equals to 0 are to be found on the surface g of x comma y comma z equals to 0 at the points where grade f is equals to lambda times grade g for some scalar lambda. So this lambda is, again I'm mentioning here, lambda is called known as Lagrange multiplier. Okay, right. Now, what other observation I just want to mention here is one of the observation now. I can say this is an observation. And I think it is easy to follow when you have seen, already you have seen that gradient f is normal to the level curve at a point P naught, okay, which lies on the curve, right? We have seen that fact. So I'm just writing, you can say, an extension of it. Okay, so suppose that this normal means it's going to be perpendicular to the velocity vector. Like, okay, so let's say, suppose that f of x comma y comma z is differentiable. So if it is differentiable, we can talk more about it in a region, whose interior contains a smooth curve, contains a smooth curve. Let's say, let's denote it by C, which is given by R of t. Okay, I'm just writing this in this way, is equals to some g of t I plus h of t j plus or just write it like instead of k I will use here. Okay, let's like in some other fashion. Okay, so let's write it as h1 of ti, h2 of tj, because g already reserved for something else, so I just don't want to use it here, h3 of tk. Okay, c is a smooth curve, means it's a differentiable curve. Okay, means you can differentiate, you can find the velocity vector. Okay, right. So whose interior contains a smooth curve. Yes. So if, let's take, if P naught is a point on C, P naught is a point on C, okay, where F has extreme values, okay, either minimum or minimum, extreme values, okay, are relative to its other values on C, okay, related to its other values on C, then it is easy to verify. Okay, I'm not going to verify that, so it's very easy. The same proof will be take place here. So then grade f, I will state it here, grade f is going to be orthogonal to the tangent vector dr by dt at p naught. Okay, so it's orthogonal to the velocity vector this one. Okay, so this will certainly tells you, and if you recall, that's grade f dot dr by dt. Now, what is that? Is df by dt. That's going to be 0 at p naught. Okay, so now how will it help you to again analyze the method of Lagrange multiplier is as follows. Okay, so we will try to use this observation again, that why we are saying again grade f and grade g are parallel to each other. Okay, when you have it one constraint. Okay, so now if so, let's say, okay, let f of x comma y comma z, let me completely write, and g of x comma y comma z both are be differentiable. Okay, be differentiable. Be differentiable. Let P naught be a point on the surface G equals to 0, where f has extreme values. Okay, has a, then I will write, has a local maximum or minimum, local minimum, locally only. Okay, minimum value relative to its other values on the surface G equals to 0. Okay, on the surface G equals to 0. Now, see, you take any smooth curve, okay, on the surface G, okay, which is passing through P naught. Okay, so f has a local maximum or minimum value related to its other values on the surface. Okay, G equals to 0, I can write here again, C equals to 0 is the surface. Okay, right. Now, this here gives you that f takes on a local maximum or minimum value at P naught relative to its values on every differentiable curve through P naught on the surface G equals to 0. So the above fact will gives you this. So just now it is on every differentiable curve, you can fix a curve C which is passing through P naught. So then it will say this certainly implies grade f is going to be the normal to the surface is going to be the orthogonal to the velocity vector or tangent vector at P naught. Moreover, I am saying here that normal to the surface G is also orthogonal to this tangent vector at P. Why it is so? Because it's going to be because see, if you have on the surface G, see, on the surface G, okay, P not be a point on this, okay, so that is already missed. So, okay, so this, that above fact implies, I'm just writing that, that outcome, okay, or observation here just now explained, okay, that the normal to the surface F is going to be orthogonal to dr by dt at P naught. So what is R? R is nothing but is a smooth curve, through P naught on the surface G equals to 0. Now, note that this is a curve. So if you, so somewhere G equals to 0 is there, okay, surface, and over which you have a curve. Let's say this is P naught. Okay, so you have a curve passing through P naught somewhere. So it should be like smooth. Okay, some curve is there. This is a curve. So you see, dr by dt is what? At P naught is nothing but the tangent at P naught. Okay. So this is going to be, so the normal to the surface, grade G, is going to be the normal to every point. So this is going to be normal to this as well. So grade G is going to be the orthogonal to this tangent line. Okay. Right? So this implies that also you can say grade G is also perpendicular to dr by dt at P. Right. So now that what these two facts will give you, grade F is also orthogonal to dr by dt, grade G is also orthogonal to dr by dt. So both are perpendicular to it. Means what? They should lie in the same direction. Okay, grade F and grade G should lie in the same direction. There's no other way. See, we are not talking about the zero surface. It's a non-zero surface. Okay. So grade F is going to be parallel to grade C. So that of this observation will tell you, this implies grade F is parallel to grade G. Okay. At P naught. Okay. We are only specific about P naught. Okay. Right. Okay, so means again you have that fact that there exists a scalar lambda such that grade F is equals to lambda times grade G at P naught, and also G equals to 0. Okay, that's subject to the constraint. Now I'm writing finally the method of Lagrange multiplier. Okay, when it has only one constraint. Okay, so the method of Lagrange multiplier. Okay, when you have a single constraint. Okay, suppose that f of x comma y comma z and g of x comma y comma z, okay, are differentiable. And I think it is easy to verify that how they will be differentiable means you have to see all the first order partial derivatives, whether they are continuous. They are continuous, you can decide the differentiability. Okay. Now, to find the local maximum and minimum values of f subject to the constraint g of x comma y comma z equals to 0, find the values of x comma y comma z and lambda, find the values of this that satisfy, or that you can say not satisfy, simultaneously satisfy the equation. So the equations grade f equals to lambda times grade g and g of x comma y comma z equals to 0. Okay, so if you have a function of two variables, okay, so you will have the same condition. So grade f equals to lambda times grade g and g of x comma y equals to 0. So z will not be there. Okay, so this is the definition of method of Laplace multiplication. Now let's try to solve problems. Okay, let's see this example. Find the greatest and smallest values that the function f of x comma y equals to x into y takes on the ellipse x square by 8 plus y square by 2 equals to 1. Now, if you look at this equation, f of x comma y equals to x into y, this is a hyperbolic plane, right? Hyperbolic surface, you can say. Okay, and this is it takes on the ellipse. So now, if you look at geometrically, okay, what will happen? So what will be possibly geometrically the greatest and smallest values that the function will take? So on the, if you xy plane, if you have here, okay, so you have some elliptic, okay, ellipse you can draw. Okay, it's ellipse, that's you have this is G, right? That's a G. And now you have this x into y equals to 1, x equal to x into y equals to 2, and so on. Okay, so you have the equation of plane and hyperbola. Okay, you have the negatives and all. So you have like this, right? Okay. Right. Now, what will be the greatest and smallest values that the function f will takes on the ellipse? So this is the ellipse. So what will be with that the hyperbola which touches the ellipse on the positive side? Okay, that will be the greatest, okay, value. Okay, and you have thus for the smallest you have this downwards. Okay, right? With which touches, okay, right? So that's going to be the possible scenario, okay, geometric. Now let's apply the method of Lagrange multiplier. So you have been trying to identify f of means minimizing, okay, or you can say we are interested in finding extreme values of f of x comma y equals to x into y, subject to the constraint, okay, subject to g of x comma y equals to x square by a plus y square by 2 minus n equals to 0. So we are interested in this. Okay, so method of Lagrange multiplier. So we can apply. So method of Lagrange multiplier implies or gives you implies that okay, the following. Okay, so find x comma y and lambda such that grade f equals to lambda grade c and g of g equals to 0. Okay, so this is what the method of Lagrange multiplier. Okay, so now if you recall, I'm just writing here f is equals to x into y. I'm writing the abuse notation. So g equals to x square by 8 plus y square by 2 minus 1. Okay, so now you can fill this here. So grade f is what? So fx, first part I component is y, j component is x is equals to lambda time. I component is 2x by 8, so x by 4. I plus gy is 2y by 2, so that's going to be 5j. Okay, so this will be this is possible. Okay, so these two sides are equal. Okay, above is possible. Only if you have y equals to lambda x by 4 and x equals to lambda y. So y equals to lambda x by 4 and x equals to lambda y. So if you use this x equals to lambda y here, okay, so because you have to solve these two equations in 3 unknowns here. So okay, so x, y, and lambda. You have to find out the lambda. So 3 equations are there, not down. G of x comma y equals to 0. Okay, so from here and these two, what we can have is y equals to lambda x is lambda y, so lambda square y by 4. So this will give you lambda equals to plus minus 2 and y equals to 0. So there are two possibilities. One is lambda equals to plus minus 2. Another possibility is y equals to 0. Okay, now the case is, so y equals to 0 is not possible, I say. Y equal to 0 is not possible. Why? Because y equals to 0 is, if it is the case, then what will happen? X is also 0 because of this second condition. X is 0. So means you have the point 0, 0, but that will not lie on the ellipse. Okay, so 0, 0 is not a point of interest. Okay, because you are trying to identify the points on the ellipse. Okay, not the interior point of the ellipse. You are trying to identify the point on the ellipse. Okay, so y equals to 0 is not possible. only cases y is non-zero means lambda's values are possibly plus and minus 2. Okay, so once you have A, this implies, so, oh, so above is possible only if you have, this is y equals to lambda x by 4 and x equals to lambda y. So this together will implies y equals to lambda square y by 4. This implies either y equals to 0 or lambda equals to plus minus 2. Y equals to 0 is not possible since 0 0 is not 0 0 does not lie on the given ellipse. Okay, so now this can be discarded. Okay, so this only possible. This implies y must be non-zero and lambda must be plus minus 2. So this implies, so y is equals to lambda x by 4. So y is non-zero. So x equals to, you can find out. So this implies x equals to lambda y. So that's going to be y equals to x equals to plus minus 2y. Now, we have identified lambda is plus minus 2 and y is non-zero, and x values as well also depending on y. Now, this x comma y, so note that the pair x comma y should satisfy g of x comma y equals to 0. So this implies means x square by 8 plus y square by 2 equals to 1. Okay, so this will imply, now since x is plus minus 2y, okay, so I can use it here. So this is going to be 4y square by 8. Okay, so 4 by 8 is 1 by 2. So y square by 2 plus y square by 2. So that's going to be y square equals to 1. This will give you y equals to plus minus 1. So y equals to 1, x equals to 2. Y equals to minus 1, x equals to minus 2. So this will give you 2 points. Okay, so this will give you, so this implies you have pair of points are x equals y equals to 1, x equals to 2, and y equals to minus 1, x equals to minus 2. So two pair of points where it will have the maximum or minimum, and it is easy now, okay, to identify the maximum or minimum values. F of x comma y is equals to x into y. So the maximum value will be here 2 into 1, that is 2, and that's a maximum. Okay, and f of x comma y equals to x into y equals to that's going to be 2. So it's only giving you maximum, right?
Sir, can't there be 4 points? Like,
No, they got 4 points.
like,
See, this
minus
method
2,
will
1,
gives you, huh?
minus 2, comma 1. Like keeping 1, y as 1, we can get plus minus 2 for x as well.
Just a second. So for, because x equals to, oh,
Plus
okay, okay. For
minus.
y equals, okay. For y equals to 1, x is plus minus 2, right? Okay, okay. So you have 4 points, right? So plus minus 2 comma 1, and you have n minus, so it's going to be minus plus 2 comma minus 1, right? Yes, right? So you have these points, right? 4 points. So you have 2 comma 1. I'm just writing all the points here. So let's write it. For y equals to 1, x equals to 2, and 1, x is also minus 2. For y equals to minus 1, Okay, you have, so if you multiply by minus, so it's going to be minus plus, right? Okay, so minus plus means you have minus 2 minus 1 and 2 comma minus. So this 2 comma 1 and minus 2 minus 1 will give you the points where it will attain the maximum, and here it will attain the minimum. Okay, minimum at, so you have two pairs, you have, whenever he has, this is have opposite sign. So 2 comma minus 1, and this is the points 2 comma 1 and minus 2. And of course, from the geometry also, right? From the geometry also, we can recognize 4 points. So minus 2 minus 1, see this side. This will be, both will be here negative, both will be positive here. So this side will give you the maximum and this side will give you the minimum. One of them is negatives. Okay, so these points you have to find out, okay, where it touches the ellipse. Okay, fine. So this is how this is the beauty of method of Lagrange multiplier. So let's try to solve. I think I have one more problem now. Yeah, so that also we can understand geometrically as well. Okay, so let's take this next problem. Find the maximum and minimum values of the function, and it will be more clear actually. If, the function f of x comma y equals to 3x plus 4y on the circle x square plus y square equals to 1 unit circle. Now it is easy to see its geometry. So x square plus y square equals to 1 is a unit circle centered at origin. Okay, so my geometry is not that good. Okay, so and what about 3x plus 4y is a line. So 3x plus 4y is equals to some constant. So from here it is easy to verify that y equals to minus 3 by 4x plus c by 4. Again, that's a generic constant, so it's going to be this. Okay, so means so what are the these this line? Okay, so you can see, you can take one or two examples here. So let's take 3x plus 4y is equals to 1. Okay, or it's like, okay, is equals to, let's say 0. Okay, so this will give you y equals to minus 3 by 4x. So x equals to 0, y equals to 0. Okay, and x equals to 1, y equals to minus 3 by 4, so downwards. Okay, so it will be to the line passing over. Now you can design other lines. So these other C1, 2, 3, 4, if you write, they are nothing but the shifting. So this will be like, okay, these are the straight lines. Means parallel only, they will never intersect. So it looks like, but my geometry is not that good. Okay, so these are the straight line. So now you are trying to identify the maximum and the minimum values of the function. So I hope that now it will be clear from here. So where it will touches the circle from the positive side, I hope this will give you the maximum. Okay, and when it touches the negative side, okay, that will give you the minimum. Okay, so this will give you the minimum. So you are straight. So let's take the help of method of Lagrange multiplier. Okay, so the method of Lagrange multiplier is, I'm just writing direct. Okay, now, so find x comma y and lambda such that grade f is equals to lambda times grade z and g equals to 0. Okay, so I can write on this side f is equals to 3x plus 4y and g equals to x square plus y square minus 1 equals to 0. Now grade f equals to lambda times grade. So grade f is 3i plus 4j. I'm writing directly now. Now lambda times grade z, that is 2xi plus 2yj. So this will give you 3. This is only possible when you have 3 equals to 2 lambda x and 4 equals to 2 lambda y, and these together will imply this is going to be x equals to 3 by 2 lambda and y equals to 4 by 2 lambda. So that's going to be 2 by lambda. Now, note that lambda is non-zero, right? Okay, so lambda should not be 0 because if lambda is 0, that grade f is a 0 vector, and we are not interested in a 0 vector. So, because why lambda non-zero criteria is required? Because this lambda is sitting in the denominator now. Okay, now these x and y should be such that they should satisfy this equation g equals to 0. So that will imply, okay, so now g equals to 0 implies x square plus y square equals to 1. Now x equals to 3 by 2 lambda, y equals to 2 by lambda. So 3 by 2 lambda whole square plus y square is 2 by lambda whole square is equals to 1. So this implies you have this is going to be 9 by 4 lambda square plus 4 by lambda square. So this is going to be 4 by a lambda square. So this is going to be 16 by 4 lambda square. I'm just making it simplified one. So it's going to be 25 equals to 4 lambda square. So this implies lambda square equals to 25 by 4. So this implies lambda equals to plus minus 5 by 2. So this will give you, so this implies lambda is equals to plus minus 5 by 2. So once you have the lambda values, then so we have x equals to 3 by 2 lambda. So that's going to be, so 3 by, so 2 lambda, this implies 2 lambda is equals to plus minus 5. Okay, so this will give you, so this will give you, this implies is equals to plus minus 3 by 5. And y equals to 2 by lambda. So 2 upon 5 by 2, so 2 will get, so it's going to be plus minus 4 by 5. Okay, now you have, so for lambda equals to 5 by 2, you have, so here you will get only 2 pairs. Okay, so that will give you, so there are x lambda equals to 5 by 2, you only have 3 by 5 and 4 by 5. When you have x equal lambda equals to minus 5 by 2, you have minus 3 by 5 comma minus 4 by 5. So these are the 2 points where it will attain, where it will touches the circle, okay, f. Okay, and the maximum value and minimum value now. So f of 3 by 5 comma 4 by 5 will give you maximum. So 3 times x, so that's going to be 3 times 3 by 5 plus 4 times 5, 4 by 5. So it's going to be 9 plus. Ishan, you have to mute yourself. So 9 by 5 plus 16 by 5, that's going to be 25 by 5, that's going to be 5. and f of minus 3 by 5 comma minus 4 by 5 is equals to 6. It's going to be due to symmetry, negative side you will get minus 5 there. Okay. So we have solved now, I think, enough problem for single constraint. Okay. So now let's now go to, if you have two constraints. So can we extend the method? Okay. So what does it mean? That you are, I wish to find local maximum or minimum, okay, or minimum of this differentiable function. You can write f of x comma y comma z, okay, whose variables x comma y comma z are subject to or are satisfied or are those variables are the points are subject to two constraints. G1 of x comma y comma z equals to 0 and G2 of x comma y comma z equals to 0, where both G1 and Z2 are differentiable. That's required. What other thing is required or necessary? Okay, that they should intersect. Okay, they should intersect at some angle. Okay, they should intersect at some angle. So means if we are saying that they should intersect at some angle, means what? That their normal should not be parallel. Okay, so that will guarantee when their normals are not parallel, there must be angle between them. So you know how to find the angle between two surfaces means you find the angle between their normals. That will give you the angle between the surfaces. Okay, so let me see. We are having again. I have to write this. Say find the extreme values of a differentiable function f of x comma y comma z equals f of x comma y comma z, whose variables are subject to two constraints g1 of x comma y comma z equals to 0 and g2 of x comma y comma z equals to 0, where both g1 and g2 are differentiable and such that grade G1 is not parallel to grade Z2. They should intersect. Now, if you recall the previous concept, what was that? You were interested in finding the extreme value of a differentiable function f whose variable are subject to one constraint, that is g of x comma y comma z equals to 0. Now, see, if you So suppose, see, you have the surfaces, you have, let's say, this one surface, okay, and one another surface. So if their normals are not parallel, they will be intersecting at some part. So that will be when they intersect. Suppose this intersects means like you have a what I can say is a some you can take cylindrical shape pipe. Okay, you can take some cylindrical shape pipe and you cut down like this. Okay, so you cut down it in that which like by a plane something. Okay, so it will intersect. So it will give you if you so it looks like this, but it will be somewhere like you will get that shape. Okay, that will give you some curve. Okay, so if that is subject to concept, they should intersect. So you will get intersect at intersection means when you cut down a pipe. Okay, when you cut down a pipe, you will get some equation of elliptic or something you will get. Okay, in this cylindrical one. Okay, now you are interested in finding the extreme value of some f other surface. Okay, subject to x, y, z also satisfied. Okay, so what you can analyze on this intersection. So this intersection will be the part of the both of the surface, right? If you intersect, if you cut it, okay, so that curve which you obtain, okay, that intersection curve, okay, that will be lies on both of the surface. Okay, earlier you had only one surface, so that's why you have taken grade f is parallel to the grade c. Now you have intersection of two surfaces and they will intersect at curve. Okay, so if you take, so the normal to this, let's take this is G1, the cylindrical one is G1, and this rectangular plane type or knife type is something C2. So this curve is C, okay, is somewhere here, okay. So you will get somewhere like after intersection, what you will get is like this. Okay, so that upper part is gone. So this is the curve. Okay, but this will be the part of the both the surface. So grade Z1 and grade Z2 at point P naught. So you are looking at the point P naught where it will attain the maximum and minimum. Okay, so and the smooth curve. This is a smooth curve. So more in generally when you cut down anything, okay, you will get obtain a smooth curve, differentiable curve. So most of the time in general, you will obtain a smooth curve. Okay, so we can without loss of generality, we can also assume that we are obtaining a smooth curve, which is differentiable. So grade G1 is also orthogonal to that dr by dt. Grade Z2 is also orthogonal to dr by dt. Now, grade F is also orthogonal to dr by dt. Now, how do we relate all these three? Means, so grade F, so which vector will be orthogonal to both grade G1 and grade G2? So means this grade F will lies in the plane, okay, which is generated by these two vectors. So you have this, you will have grade F is going to be some lambda time grade Z1 plus some another parameter mu time grade Z2. It will lies in this. Okay, so this is the extension of method of Lagrange multiplier. Okay, when you have two constants. So if you now in the similar fashion you can generate you can generate a method for Lagrange multiplier for with multiple constraints. Okay, right. So now So what the method of Lagrange multiplier with two constraint states is means that grade F is lambda grade equals to lambda grade G1 plus mu times grade Z2, and you have G1 equals to 0 and Z2 equals to 0. So you have to find X comma Y comma Z lambda mu, 5 things. Okay, subject to these 3 conditions. Okay, and that will solvable. That will be solvable. So let's take one example here. Okay, so let's take one example. The plane x plus y plus z equals to 1 cuts the cylinder x square plus y square equals to 1 in an ellipse. In an ellipse, okay, find the points on the ellipse that lie closest to and farthest from the origin. Okay, so how do you handle it? So just now I explained you. So you are trying to identify or extreme values of this following function. The point closest to and farthest from the origin, that's like where again like x square plus y square plus z square, subject to the constraints of G1 is equals to x plus y plus z equals to 1. So minus 1 equals to 0. And G2 equals to, let's circle x square plus y square minus 1 equals to 0. It's a cylinder. Okay. Now, means the method of Lagrange multipliers tells you that find x comma y comma lambda, x comma y comma z comma lambda and mu such that grade f is equals to lambda times grade z1 plus mu times grade z2, g1 equals to 0, g2 equals to 0. Okay, so if I write, I can write here f is equals to x square plus y square plus z square, g1 equals to x plus y plus z minus 1, g2 equals to is x square plus y square minus 1 equals to 0. Okay, so this relation will give you 3 equations, and this is our 1 or 2, 3 to 5 equations, 5 unknown. So that will give you solution. Okay, so grade f is again 2xi plus 2yj plus 2zk is equals to lambda times grade c1, so I plus j plus k plus mu times grade z2 is 2xi plus 2yj. There is no z component. Okay, now you compare. So this implies, so I component on the left side is 2x, on the right side is lambda plus 2x mu. Okay, so I'm comparing. So 2x equals to, it is possible only when 2x equals to lambda plus 2 mu x, 2y equals to lambda plus 2 mu y, 2y equals to lambda plus 2 mu y, And third equation is 2z equals to lambda. 2z equals to lambda. So these are the three equations. Okay. So now let's use this 2z equals to lambda. Okay. So if you use 2z equals to lambda here and here, so what you will observe is going to be 2x equals to 2z plus 2 mu x, 2y equals to 2z plus 2 mu y. So this will give you, so 2 will get cancelled on both sides. And what you will observe is x equals to z divided by 1 minus mu, y equals to z divided by 1 minus mu, provided mu should not be equals to 1. Okay, so there are only two possibilities. Okay, if you want to satisfy these two relations, is one is mu equals to 1, then z has to be 0. Okay, okay, so this above will rise to, so if I don't write this first, okay, so what is here is I'm just writing, this implies 1 minus mu x equals to z, okay, and 1 minus mu y equals to z. So what this will give you, this implies, so there are two cases, mu equals to 1, z equals to 0. One case is this, mu is not equals to 1 and x equals to y equals to z divided by 1 minus mu. Now, so z equals to 0 means mu equals to 1. Okay, that case, let's take case mu equals to 1 means z equals to 0. So in that case, what will happen is you have equation of G2 is f, so x and y such that x square plus y square equals to 1 and x plus y plus z equals to 1. But z is 0. So this implies x plus y is equals to 1. So you have two equation in two unknowns. So you can use this here. And so what it implies is x square plus y square. Y square is y is 1 minus x. So 1 minus x whole square equals to 1. Okay. So if you open it up, what will you observe is going to be 2x square minus 2x plus 1 equals to 1. So 1 will get cancelled. So from here, 2x square minus 2x equals to 0. So 2 will also get down. We have x into x minus 1 equals to 0. So this implies x equals to 0 or x equals to 1. Now this implies x equals to 0 or x equals to 1. So what it gives you, x equals to 0 implies y is equals to 1. And x equals to 1 implies y equals to 0. So what are the points you observe now is z is 0. So 2 points, right? And x is 1, y is 0. X is 0, y is 1. So 2 points you observe. Okay. Now both will lie on the, you can see both will lie on the G1 and Z2. Okay. Now case 2. Case 2 is mu is not equals to 1. Means z is non-zero, obviously, and x equals to y equals to z divided by 1 minus mu. Okay. So now equation says you that x square plus y square equals to 1. What it will give you is, since x's and y are same, is going to be x square plus y square equals to x square plus, just a minute. So y equals to x. So we'll give you x square plus x square equals to 1. So this implies 2x square equals to 1. So x equals to plus minus 1 by root. Okay, now x equals to plus minus 1 by root 2 means y is also plus minus 1 by root 2. Now z value you have to find out. So for z, you have x plus y plus z is equals to 1. Okay, now x plus, so this implies y is x, so 2x plus z equals to 1. So this implies z is equals to 1 minus 2x. Now, what is x is plus minus 1 by root 2. So this is equals to 1 minus 2 times 1 by root 2 whenever x equals to 1 by root 2. And you have 1 plus 2 by root 2 whenever x is minus 1 by. So you have the values now. Okay. So what are the pairs now you obtained is so you have obtained now x equals to plus minus 1 by root 2. So x is 1 by root 2, y is also 1 by root 2. And in that case, z is x 1 minus 2 by root 2 is 1 minus root 2. 1 minus root 2. Okay. Another pair is minus 1 by root 2, then minus 1 by root 2. And you have 1 plus root 2. Now you have 4 points. Okay. 0, 0, 1. Sorry, no. 0, 1, 0 and 1, 0. Okay. Now you can you have now equation f of x comma y comma z. You have the 4 points p1, p2, p3 and p4 where you can see which one will give you the maximum value, which one will give you the minimum value. Okay, so this p3 and p4 will give you the, I think, unit distance, right? Yes, 1. Okay, and from here one of them will give you the other values. Okay, so that's going to be, so x square plus y square will not make any difference here, only will give the difference here. Okay, because f of x comma y comma z is x square plus y square plus z square. Okay, right. So I think we have completed our method of Lagrange multiplier. Okay, and I have tried to explain you geometrically what it essentially does. Okay, with the constraints. Okay, right, fine, and thank you. And I think we will take care of the that tutorial problem left. Okay, that 5th problem. Okay, which one left during the previous tutorial. Okay, in the next class. Okay, and right. So if you have any other question, you can ask. Yes. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.